My name is Kritika Iyer, and I will be presenting our paper, Statistics Informed Correspondence Prediction Directly from Unsegmented Images. This work was done in collaboration with J.D. Adams and Dr. Shireen Alabian at the Scientific Computing and Imaging Institute, University of Utah. Here are meshes representing the left atriums segmented from cardiac MRIs. Unlike geometrical shapes that have equations to describe them, we do not know the parameters that define the shapes of such anatomical structures. Statistical shape modeling, or SSM, is a technique that learns shape representation directly from data in a way that reveals important statistics. SSM can be used to measure and quantify shapes in relation to a population of shapes, or to answer medical questions related to disease diagnosis or detecting pathology. Explicit shape representations, such as point distribution models or PDMs, are widely used for SSM. PDMs are characterized by a dense set of correspondences describing anatomically equivalent points across samples. This is a typical pipeline followed by conventional SSM tools, which includes steps like segmentation, resampling, registration, and correspondence optimization. Conventional pipelines for shape modeling from imaging data demand significant manual and computational resources. Additionally, these methods require repeating the entire modeling pipeline to derive shape descriptors from new imaging data. Deep learning models such as DeepSSM and TLDeepSSM have shown promise in streamlining the construction of SSMs from new data by predicting correspondences directly from images. However, they require established PDMs obtained from traditional shape modeling tools for training. Therefore, these methods use supervised losses to train the network. Dependence on established PDMs obtained from conventional optimization pipelines introduces linearity assumption, affecting the ability of the models to represent complex anatomical structures. Moreover, volumetric images may present additional challenges such as noisy and unreliable image features and poorly defined anatomies, which can impede feature extraction. Therefore, integrating shape prior information is important to guide and constrain learning for the correspondence estimation task. To tackle these challenges in image-driven SSM tasks, we present Statistics Informed Correspondence Prediction, or SCorP. SCorP predicts shape correspondences directly from images. Our model bypasses the requirement of predefined PDM for training and leverages multi-view data of paired volumetric images and surface representations. Using a student-teacher framework, the shape prior from surface representation acts as a teacher for the image-based learning task. SCorP distinguishes itself with its minimal requirements, relying solely on surface representation for training while avoiding adherence to the linearity assumption. SCorP's architecture integrates a surface branch and an image branch. The surface branch consists of a surface autoencoder and an implicit field decoder, which learns a shape prior from surface representation. The image branch includes an image encoder which is guided by the shape prior to predict meaningful features useful for correspondence estimation directly from images. The surface branch or teacher uses the same architecture as Mesh to SSM that includes a surface autoencoder to capture the low-dimensional representation of each surface mesh. This autoencoder employs dynamic graph convolution HConv blocks to extract local geometric features, which are then used by the implicit field decoder to predict correspondence points that describe the shape. IMNet, or the implicit field decoder, uses a template point cloud to predict shape correspondences by transforming the template to match each shape based on its latent representation. The surface branch is trained by minimizing the chamfer distance between the predicted correspondences and the mesh vertices, along with the mesh reconstruction loss. The image branch consists of an image encoder that learns to align its features with the shape prior from the surface branch whose weights are frozen. This alignment ensures the image features are semantically meaningful and consistent with the surface features. Alignment is achieved through a regression loss that minimizes the difference between the two sets of embeddings. In the final stage, the image branch refines the predicted correspondences to match the surface meshes better. This refinement involves minimizing the chamfer distance between the predicted points from images and the actual mesh vertices. For our experiments, we use our in-house left atrium dataset and the public liver datasets containing highly variable shapes. We use the following metrics to assess SSM correspondence accuracy: compactness, quantified by the number of PCM modes required to capture 95% of the variation. Generalization measures how well the SSM from training data extrapolates to unseen data quantified by the reconstruction error for the held out samples. Specificity evaluates the average distance between sampled and existing training correspondences. Point to mesh and chamfer distance measure how close the predicted correspondences are to the mesh surface. And surface to surface distance evaluates mesh reconstruction quality. We compare our model with the state-of-art supervised models DeepSSM and TLDeepSSM. We also include a baseline model that predicts correspondences from images using only the image encoder and the implicit field decoder without the shape prior. The poor performance of the baseline model conveys the importance of introducing shape prior. SCorP outperforms the other models in terms of chamfer distance. SCorP is the best performing model with respect to point to mesh and surface to surface distance for the LA dataset, and shows competitive performance for the liver dataset. SCorP provides the best compactness for both datasets, suggesting strong correspondence, and showcases comparable specificity and generalization. Despite being an unsupervised method, SCorP identifies same modes of variation as other methods. Additionally, our model shows detailed and smoother variations as compared to other methods highlighted by the boxes. We also analyze the robustness of all methods across different training dataset sizes. SCorP consistently outperforms DeepSSM and TLDeepSSM, indicating its robustness and superior generalization ability. In conclusion, SCorP increases the feasibility of SSM in clinical scenarios by bypassing time and labor-intensive steps of building pre-optimized PDM for training. By integrating the shape prior information, it effectively guides the image-based network to predict features representative of the correspondence prediction task. We would like to thank the National Institute of Health, Division of Cardiovascular Medicine at the University of Utah, and the ShapeWorks team for making this work possible. Thank you.